lesson 2 for chapter 7. We've been talking about angular displacement, theta, angular velocity, omega, angular acceleration, alpha. We had the same kinematic equations in angular motion as we had in linear motion, except we had the symbols from the Greek language instead of the English language. Now, everything that we were talking about in lesson 1 were things spinning on an axis, spinning around a central axis, or axle of rotation, we sometimes call it, like a wheel spinning on its axle. Now we're going to talk about moving in a circular path, where the center is some distance radius from every one of the points that the object is traversing. So we're going to come up with a name for this kind of acceleration. It's called centripetal acceleration. You might wonder, well, where in the world is centripetal velocity? And we'll talk a little bit about that, or at least allude to it later. But right now we want to talk about a constant linear speed moving in a circular path, and therefore its direction is changing. And because its direction is changing, even though it has a constant speed, it has to be accelerating because it's changing direction. Because remember, velocity is a vector, a change in displacement over time, or a change in direction. And acceleration is what we call a change in velocity, when either the magnitude of the velocity changes or the direction of the velocity changes, like when you go around in a circular path. So when we look at this equation right here, if we're going at a constant speed, you might say, well, if I take my final velocity and then subtract my initial velocity, that should equal 0, because the speeds are the same. Well, it is true that the speeds are the same, but the directions are not. Therefore, the velocities are not identical. Therefore, the numerator, which is the difference in the final and the initial velocity, cannot be equal to 0. So when we come up to the top of the page, you'll see a picture from a drone looking down at a car that is going to be moving in a certain direction. It looks like it's moving clockwise, which would be, again, clockwise would be in the negative direction, if you remember the convention from the first lesson. And if for some reason it should suddenly lose all traction, its tangential velocity, it would fly off in that direction because of its inertia, because there would be nothing holding it in place anymore. Now, these vectors have the same magnitude, as I said a minute ago, meaning because they have the same speed, but they do not have the same direction, therefore their difference cannot be 0. And we can represent that right here. We can have, if my car is at this point in its path going like this, and then at some time later it is now this way, you'll notice that these two vectors that I've traced in red have equal magnitude, but they're pointing in different directions. Now, in order to derive this equation right here, I have a separate derivation, a separate sheet of paper that you should be able to find on Canvas that shows how we come up with equation 7.13 by comparing two triangles. One triangle is a triangle of lengths, and the other triangle down here is going to be a triangle of velocity vectors. And you'll see that on that sheet of paper. I'm not going to spend time on it in this screencast, but suffices to say that as we work through these similar triangles, one made out of distances and the other made out of velocity vectors, we end up with this equation right here, that the centripetal acceleration, the acceleration towards the center, equals the velocity squared divided by the radius. And you might remember that velocity equals r omega. We had that in lesson number 1 as well. So v squared is going to be r squared omega squared, which is how we get this equation right here. And you can see that in this equation 7.17, one of these two r's in the numerator cancels out that r, and we get centripetal acceleration equals the radius times omega squared. Now, as we continue on, I should mention one thing that will be coming up in a minute, and that is if I multiply this equation by mass and this side by mass, both sides by mass, you might recognize that mass times acceleration is a force. This is my centripetal force, which we'll talk about in a minute. And centripetal force is not a new kind of force, but it is a force that acts towards the center for any one of a number of different reasons, which I'll talk about shortly. So an acceleration can only occur if there is some force that is present. An unbalanced force causes acceleration. It either causes a change in its velocity in terms of the magnitude of the speed or a change in the direction of that velocity. And this particular acceleration, since it's directed towards the center of the circular pathway, is called a centripetal. Centripetal meaning center-seeking force. Now, if we think about the fact that I might have if my pathway is something like this, and this is my center-seeking force of an object. Let's say it could be a planet being held in place by gravity. It could be a solid object that we're spinning on a string, or it could be a car going around a curve and being held in place because of friction with tires against the road. Any one of those could be responsible for the centripetal force. Its tangential velocity would be tangent to the circle, and this would be my, and so when we talk about acceleration, this would be my tangential acceleration, because forces are mass times acceleration. We can ignore the mass here, and so this would be a t. And this centripetal force, if we cancel out the mass or ignore the mass, we're going to have a centripetal acceleration. If we add these two vectors together, then this is my resultant vector right there for those two accelerations. And we could solve for this total acceleration A using the Pythagorean theorem. Now at this point, it would be a wise idea to pause and see if you can do the quick quiz and then check your answers in the back of the book. Now let's look at this first problem at the racetrack. So we have a race car accelerating uniformly. In other words, there's not a change in acceleration due to a change in magnitude of velocity, but there's a change in direction. It says a race car accelerates uniformly from, I take that back. We are changing our speed as well as direction. So that's good to know. So we have a speed of 40 meters per second, and we are accelerating up to 60 meters per second at the same time that we are going around the track in a counterclockwise direction. So that would be a negative sign if we had to indicate the direction of the car in the problem. We're given the radius of the track. It's a pretty big curve, 400 meters. So it's a very slow, gradual curve, about the length of 4 soccer fields. And so we have 3 parts to the problem. Part 1 is when the car reaches a speed of 50 meters per second, which is halfway between the initial speed and the final speed, calculate the magnitude of the car's centripetal acceleration, then calculate its angular velocity, and then calculate the magnitude of its tangential acceleration. And so when we go to solve this, let's look at part A, calculate the magnitude of the centripetal acceleration. All we have to do is take out our equation for centripetal acceleration, which is our average velocity squared divided by the radius. That's pretty straightforward, no problem. Part B, calculate the angular velocity. Well, the angular velocity, you might remember the identity earlier on that said your linear velocity equals your radius times your angular velocity. So we can solve for the angular velocity pretty easily by plugging in my speed and dividing by the radius. And I get this answer. Then in part C, calculate the magnitude of the tangential acceleration. And that would be the speed if all of a sudden there was absolutely no friction on a flat track, so there isn't even a normal force like you would have on a banked curve. We'll look at a problem like that in a minute. And so, in other words, the car loses all traction. The centripetal force would, at that moment, go to zero, and it would go flying off the track at that speed of the difference in speed right here. And it took 5 seconds to go from this speed to this speed. And so we see that its acceleration is 4 meters per second squared. That would be the tangential acceleration at that point. And then finally calculate the magnitude of the total acceleration at that point. And the total acceleration would be using the Pythagorean theorem. And we just did this, you recall, on the previous section. And we're going to solve it for A, and we get 7.42 meters per second squared. Now, let's talk about Newton's second law, which you know is F equals ma. You also know that unbalanced forces cause acceleration. And so when unbalanced forces do not equal zero, there must be acceleration, and that must equal ma. And we're going to be talking right now about uniform circular motion. So that means the circular motion is the same all the way around the circle. Just as acceleration and force are vector quantities, so are centripetal acceleration and radial forces vector quantities. So the first thing we have to recognize is that centripetal force is not a new kind of force, but it is whatever that force is that's holding an object in its circular path around some center point. So in the example over here, my centripetal force is the tension. And I'll do F sub t for the force of tension in this example. Or if this object happened to be a planet, then what's holding it in place would be the force of gravity. In that case, my centripetal force is the force of gravity. So you get the idea. Let's do one more example. Let's suppose that this is a car. So I'll make my car blue. And if this becomes a car that's traveling, it's the friction that is holding the car in the circular path around the corner. It's the friction. So the centripetal force is not a new kind of force, but depending upon the problem, it could be the force of tension, the gravitational force, the force of friction, whatever the force is that's holding that object in its circular path as it goes around some central point. The central point could be your hand holding the string and therefore tension. It could be an object like the sun holding a planet gravitationally in its orbit, or it could be the force of friction that's holding the tires against the road. And even though it doesn't seem like that would be a force acting towards the center, that's how it's displayed. So, as I did earlier, when I had the centripetal acceleration equals v squared over r, and I multiplied both sides by m, I get this equation right here. Pretty important equation as far as centripetal force is concerned. You would be given it on a test. Keep in mind that when the centripetal force is not sufficient to hold an object in its circular path, then the object is going to fly off tangentially, and that would be because of inertia. So, for example, if an object is moving, let's go counterclockwise like this, and let's say it's a ball at the end of the string, and let's say that, so here's the ball, and this dotted line will be the string holding the ball in place, and let's say that the string suddenly breaks. Well, the ball does not fly off like this, it flies off tangentially. This is a common misperception, though I doubt any of you would have that. It flies off tangentially. And that's because of its inertia. It's going to keep on moving in a straight line unless an outside force, that is to say a centripetal force, acts on it to hold it in its circular path. Now, you may have heard the term centrifugal force. In fact, in chemistry, we often use a centrifuge. And a centrifuge is a device which can spin test tubes very, very, very quickly, thousands of times a minute sometimes, in a circle. And the idea is if there's any type of precipitate or solid in solution, the inertia of that solid will, it'll try to go in a straight line, and eventually it'll end up being pushed to the bottom of the test tube. And so you'll get some sediment or precipitate at the bottom of the test tube when you stop the centrifuge and take the test tube out. Now, the name centrifuge is probably a misnomer. It probably should have been called a centripetal machine instead of a centrifuge, a puge or something, instead of a centrifuge, because in this case, there is no such thing as a centrifugal force. Now, in other situations not having to do with centripetal forces, there is something that we call a center fleeing or a center's avoiding force, a force that wants to take it away from the center. And like my original arrow up here would be a centrifugal or center fleeing, because it's going in the direct opposite direction from the center. And one example of that would be if you have two particles, and I need to erase some stuff here so you can see it. If I have two particles, and they have the same sign, they're both positive particles, maybe both protons or both nuclei, or maybe negative particles, they're negative ions, or maybe they're electrons, they will repel each other. They will try to move in opposite directions from each other. And you can see we're not even talking about a circular path here. That could be called a centrifugal or center fleeing force, because the center would be the point in between those charges. Let's see, if an object is falling towards the surface of the earth, and here it comes. How you like that whistle? And it's falling towards the center of the earth blocks it when it hits the surface of the earth. And so the normal force, where the earth is pushing up once the object hits it, would again be a centrifugal or center fleeing force in the opposite direction. But once again, this is not in the context of centripetal forces and curvilinear motion. So as far as curvilinear motion is concerned, objects moving in a curved path, centrifugal forces are fictitious. They do not exist. Now, a couple of points about convention. Because forces are vectors, we need to designate whether they are positive or negative. And scientists have chosen, and it sounds kind of logic to choose it this way, this is a convention, that any force acting towards the center let's fix that, towards the center. And for some reason, every time my hand rests on the bottom of my iPad, it seems to erase stuff. There we go. Sorry for the delay. A force acting towards the center, by convention, is called a negative force. So centripetal forces are generally negative forces. Sometimes that negative sign is necessary in the context of the problem. Sometimes we're thinking in terms of absolute value of the magnitude of that force. And then a force acting away from the center, there we go, is by definition positive. And of course, if you think about it, if this is the surface of the Earth and we're moving an object higher and higher into the sky, that's adding work to it. We're doing work on it. We're increasing positive potential energy. And then if the object begins to fall back down again, it's moving in what we would call the negative direction towards the surface of the Earth. Its potential energy is going to zero. That might be one of the reasons why they chose this convention. In any case, whenever centripetal force, be it tension, be it gravity, be it friction, whenever the centripetal force is the force keeping an object in its curved path, therefore there is centripetal acceleration. It is the unbalanced force. And the summation of unbalanced forces, here's the summation of my unbalanced force, must equal ma. And ma, A here, is my centripetal acceleration. And my centripetal acceleration, if you recall the equation from earlier on, is v squared over r. So that's where they get this. Now, just a little side light, a little tangent. If a person is going to be in outer space for any length of time, and we've had some astronauts out there on the, not the space shuttle, but the International Space Station for quite some time, and because they're not experiencing any gravity in the small container that they're in, if you want to call it a container, they gradually diminish in muscle mass and calcium in their bones, and they can get immeasurably weaker. And it takes a while to get all of that strength and muscle tone back. But if we could make this space station bigger and bigger and bigger, so that it is spinning like you see here in the picture, that spinning will create a normal force, and they drew it in blue, pushing on the individual in the space station. And so the individual can't tell the difference between gravity and the normal force of the sides of the space station pushing up at them. And so they're experiencing gravity. Their muscles are working against the gravity. And biochemically, the bones are accumulating calcium. And so they have a much greater chance of remaining healthy and strong in lengthy stays in outer space. Now, if your space station has a relatively small radius, you have to spin it really, really fast in order to simulate Earth's gravity with this normal force. So it's been proposed that what if we made a gigantic space station that, let's say, is a half a mile or even a little more than that, a kilometer in radius. Then it doesn't have to spin very slowly, very fast at all. In fact, it would be spinning so slowly that you might not even notice that you're spinning, and you wouldn't have any nausea from that. So let's take a look at another reminder that you should have your seatbelt buckled. So calculate the frictional force that causes an object to have centripetal acceleration. And so this frictional force is going to be the centripetal force, because it's the force that is holding the car on the track as it goes around the bend. And I remember as a boy, I think I was in 8th grade, somewhere after 8th grade, our family was in a very serious car accident outside of Indianapolis. We were going around a corner in the rain. The tires lost friction, so the centripetal force stopped, and we started going in a straight line, and there was a telephone pole here, and my dad managed to avoid the telephone pole, but oversteered and ended up hitting the telephone pole on the other side. And I was sitting right in the back seat on the driver's side, and the telephone pole hit right where my mom was sitting. But I recall, I don't know how I remember this, I recall that my dad reached over, pulled mom toward him, and one of my sisters was in the very back of our station wagon without a seatbelt. She came flying forward, and Dad stopped her, and I had my seatbelt on. No, excuse me, we didn't have seatbelts in the back seat back in those days, and so my inertia took me right through the door, and I landed on the ground here in a pile of glass with a kind of a bruised, bleeding side. Everybody else went to the hospital to get checked up, but I stayed with my dad, and we did not want anybody else to see that car because it was totaled. And God was very gracious, and none of us was seriously hurt other than me a little bit. But so I wear my seatbelt. In any case, pardon that throwback from ancient history last century. So what do we know in this problem? We know in this problem that a car is traveling at 30 miles per hour, which is 13.4 meters per second. Now, of course, I'm not going to give you the metric. I would give this to you in miles per hour and let you do the conversion into meters per second, because that's just the kind of teacher I am. I'm concerned that you always know how to do dimensional analysis and that you pay attention to details. So I'm a nice guy. You'll thank me later. And make your charitable donation to the science department. Now, the radius of this curve is 50 meters. In other words, that's the distance of about half of a soccer field. And we are given a coefficient of friction. So when we go to solve this problem, way back in section 7.13, my centripetal acceleration is v squared over r. If I multiply both sides by m, you recall, again we get centripetal force equals v squared over r times m. And that centripetal force is the unbalanced force causing the centripetal acceleration. In other words, the summation of my forces in the x direction. This is the x direction this way, and this is the y direction. The summation of the forces in the x direction is this force of friction, which is the centripetal force. They're using lowercase f with an s to be the force of static friction. And I would probably do F as a force, F for friction, and maybe a little letter S to designate static, though it's almost always static. I'm sorry, that is not true. Most of our problems have been kinetic, but in this case, we're talking about static. Now, given that, then when we come down to, I just showed you this part right there. Now, when we come down here in the y direction, the up force, which is the normal force, must equal the down force, which is the force of weight on the track. Again, the track is not banked at an angle, but it's flat on the surface. Theta equals 0. And so the summation of my forces in the y direction equals 0. So we say that the normal force equals the weight. So we can substitute mg in for n. We can substitute mg in for the normal force, and therefore that mg shows up down here. And so we have my centripetal force, mv squared over r, equals my mu times the force of weight. We can cancel out the negative signs, and now we can solve for the coefficient of friction, 0.366. Now this is a good reminder down here. A rubber tire on dry concrete is pretty close to 1. But if it's wet or icy, it diminishes by a factor of up 5, potentially, or even worse, down to 0.2. So you really must adjust your speed when the roads are wet or icy. Now, this problem here is maybe the hardest one in this section. And this time we're going to have a banked curve. And you can see that my banked curve is right here. And we have an angle of theta right there. Now, they made this problem easier because you'll notice there's no friction, which is kind of silly. Of course, there's going to be friction. And it would be a much more interesting problem if we did put friction in there. Because if we did put friction in there, then you would have mu equals the force of friction over the normal force. And you'd have to be given, for example, the value of mu, because you would need a third equation to take care of your all of your different unknowns. But we're going to be neglecting friction here, so we can pretty much ignore that. So now that means that my force acting towards the center, this one right here, is going to be a component of the banked curve. And the component of the banked curve is this component right there. Notice that when we say it's acting towards the center, we mean it's acting parallel to the surface of the earth. We do not mean it's acting downward. Common mistake. It's not acting downward, it's acting horizontal to the surface of the earth. And so my centripetal force is the unbalanced force. If you think again about the summation of my forces in this direction, must equal ma. Ma is mass times the centripetal acceleration, and that is, in this case, the horizontal component of my normal force. Now, another thing you should notice here is oftentimes when we've solved problems about something on an incline, we made the incline the x-axis, and we made the normal force along the y-axis, and then we componentized the weight vector. We are not doing that this time. We are not adjusting our axes. We're going to keep our axes horizontal as x, vertical is y. So therefore, the vector that we are going to have to componentize is my normal force, which they use it this lowercase n for that. And I've componentized it in the red, as you can see, Fn sine theta for the x and Fn cosine theta for the y. So when we come down here, we can see that the summation of the forces in my x direction, is going to be the unbalanced force, which is the centripetal force, which is the Fn sine theta. And now when we go to solve our problem, we can keep in mind that the summation of forces in the y direction, up and down, must equal 0, because obviously the car is not going to be floating up or crashing through the surface of the earth. So the down force, Fw, must equal the upward force, which is the component of the normal, unlike we've had in previous chapters. Fw equals Fn cosine theta. So when we put these two equations together, my n cosine theta and my weight, we get a when we solve this equation for n, and I like f sub n, but when we solve this equation for n, Fw, of course, is mg, and they use the lowercase n, and when we solve this equation for n, we get this thing in the circle. And then we're going to plug this thing in the circle down here, because this is the unbalanced force. The unbalanced force is a centripetal force. The summation of the forces in the y direction equals ma. It's the unbalanced force, and that unbalanced force is a centripetal force. And we are going to plug in for the normal there, which is, there's the normal way back up there, Fn sine theta. We're going to plug that in, mg cosine theta in for n, and now I have sine theta over cosine theta, which is tan theta. And so my centripetal force equals the weight times tangent theta as the absolute value. And the negative sign, of course, means it's acting towards the center. It doesn't mean like equal and opposite. Now, moving on a little bit farther, when we divide both sides of this equation by m, you can see that the m's conveniently cancel, which you've seen a number of times now, where it turns out mass doesn't make any difference. And so my acceleration equals gravity times tangent theta, and which is 31 degrees, and I plug my numbers in my centripetal acceleration acting towards the center, that's the negative sign, is 5.89 meters per second squared. And then I can find the speed of the race car. The speed of the race car is where I'm going to solve for v. And again, remember your centripetal acceleration is v squared over r. And let's erase, oh, come on. There we go. Erase that mess that I made. And so v squared, much nicer, v over r. We solve this equation for v, and we get 43.1 meters per second squared as my, that's my velocity. And it looks like they made a mistake right there. That squared sign should not be there. Shame, shame. All right. Now, the book points out, of course, that you have both a steeply banked curve and you have friction. And this problem ignores the friction, though it would be an important consideration. All right, another problem, riding the tracks. Now let's begin with a mental experiment. Imagine I'm standing in front of the room with a string that is 1 meter long and it's got some metal washers tied at the end, and I'm swinging it in a vertical circle. So the masses, the metal washers are above my head, and let's say they're swinging counterclockwise to my left, and they're going down to the bottom, and then they come up the other side, and I'm swinging them around. And let's say that I begin to reduce the tension, and I begin to slow it down so that by the time the masses are over my head, they just barely can keep the string taut. In other words, my normal force is, or I should say this force holding them in place, it's a force of tension, I should say, is going to zero. The force of tension is approaching zero. The string, if it was any slower, the string would begin to get limp and the masses would begin to fall down instead of continually moving counterclockwise, keeping the string tight. So we want to look at the situation up there. We want to look at the situation down there in this problem. And by the way, there's something like this in the handout that you have on Canvas. So we're going to find the speed at the top of the loop. And at the very top of the loop, the force of tension is going to zero. And so the only forces acting on the object at the very top would be the fact that, let's come back up here, when the cars are up here, you have the force of weight acting down, okay? And you also have the centripetal force the MAC, and these have to equal each other. What I should say then is that my centripetal force is no longer due to the force of tension, but only due to the force of weight. So in this particular case, the force of weight alone is the centripetal force. So when we plug in mv squared over r for my ma, the centripetal force, and here is my weight down there, because by definition, this is this. We're not saying they're equal and opposite. We're saying the centripetal force is the weight. The negative signs cancel. The masses cancel. When we solve for the velocity at the top, the minimum velocity, we get this equation right here. And this is a pretty significant equation. Let me give you an illustration. Let's suppose this is the Earth and we have a satellite that's way out here orbiting the Earth. And we want to know what's the minimum speed of this satellite. If the speed were going any faster, the satellite would be slingshot into outer space, probably get captured by the sun and get burned up, and you hate it when that happens. Or if the speed were any slower, instead of going around the Earth, it would begin to spiral into the Earth and probably burn up in the Earth's atmosphere. And you hate it when that happens. So you want just the right speed. What is that minimum speed that's going to keep it in orbit? And the answer is the square root of gravity times r. But the interesting thing here is that r now becomes this distance right here. R becomes the distance that the object is above the surface of the planet, we'll call it d, and plus the radius of the Earth. Also, we have to keep in mind that g is no longer 9.80, which would be on the surface, but g is going to be substantially less way out there. So in order to use this equation that I put in the box in blue, I would have to calculate the new g, the gravity on the satellite out in space, and make sure that the r represents the total distance from the center of the Earth. That's just a heads up, just in case you see a problem like that. Let's say, just speculating here, on a test. So, now coming down to part B, find the speed at the bottom of the loop. And so we're going to be using the work energy theorem, the wet theory, the work energy theory, keeping track of our energy along the way. So when we look at the very top, back to the top now, we can see that I have two kinds of energy. I have the kinetic energy, which the object has tangentially moving, and we also have the potential energy, which is the energy it has due to its position above the Earth. It doesn't matter that the two arrows are pointing in the same direction. That's the total energy I have at the top. Now, substituting in, back up to this equation here, if I take the equation in the blue box and square both sides, I get v squared equals gr. And so I'm going to plug that in for v squared. This v squared, I'm going to plug in gr instead. And then my mgh, the potential energy right here, my height is going to be the diameter of my circle. The height is going to be this whole distance right here, from the top to the bottom. So that's 2 times the radius. That's the diameter, 2 times the radius. And so when I simplify this equation, you can see that my energy at the top is 2.5 times its weight, mg, times the radius. The energy at the bottom is 1/2 mv squared. And remember, the speed at the bottom is a lot faster than the speed at the top. There is no potential energy because the potential energy went to 0. So let's equate those two. Let's take the energy that I had at the very top, which was in the box, and that becomes the energy at the very bottom. And when I solve this for the velocity at the bottom, I get the square root of 5 times gravity times r, the radius of the circle. And I can plug my numbers in. Then in part C, find the normal force on the passenger at the bottom. The passenger at the bottom is going to feel like there's some weight, even a different weight than what the passenger is used to, like when you go up an elevator or when you go on a roller coaster ride, like in some of the pictures that you've seen. So when we look at this problem, we see that, again, the summation of my forces in the y direction, equal ma, and that ma, mass times angular acceleration, is known as a centripetal force. Not angular acceleration, the centripetal acceleration is a centripetal force. And we can see in this problem that my normal force now, minus the force of weight, my bigger force minus my force of weight gives me my centripetal force. And so we're going to rewrite that identity right here, up here. And so here, and rearrange my terms. So if I subtract the centripetal force from both sides, I get that. If I add the force of weight to both sides, I get mg. And if I subtract the normal force from both sides, I get that n. And now, of course, I'm just going to go ahead and plug my values in again. So I'm going to solve this equation for n, and I get 6 times the weight. Or we could say you're pulling 6 Gs. Now, the last thing in the section on today's screencast is the fictional force of centrifugal force when you have something moving in a curved path. If you're on a merry-go-round over here that's spinning counterclockwise, okay, which would be in the positive direction, remember, and all of a sudden you jump off or you fall off or whatever, you're going to move in a straight line tangential to the circle. You are not going to go this way. And so you're going to have a tangential velocity at that moment as you leave the merry-go-round. So there is not such a thing as a centrifugal force that pushes you out that way. And even people that know that they would go this way think that's a centrifugal force instead of the centripetal force, but that's not true. That is just inertia pulling you or sending you in the direction. Hopefully you don't get hurt. So we're going to stop right there, and the next screencast will pick up on how all this relates to Newtonian gravitation.